Hello everyone, I am Muskan from Chemistry Honors. My roll number is 21. Today I am going to read out the chapter P block elements. Group 15 elements. Group 15 include nitrogen, phosphorus, arsenic, antimony, and bismuth. As we go down the group, there is a shift from non-metallic to metallic through metalloidic characters. Nitrogen and phosphorus are known metals, arsenic and antimony metalloids, and bismuth is a typical metal. Occurrence. Molecular nitrogen comprises 78% by volume of atmosphere in Earth crusts. It occurs as sodium nitrate and potassium nitrate. It is found in form of protein in plants and animals. Phosphorus occurs in minerals of apatite family, which are main component of phosphate rocks. Phosphorus is an essential constituent of animal and plant matter. It is present in bones as well as in living cells. Phosphoproteins are present in milk and eggs. Arsenic, antimony, and bismuth are found mainly as sulfide minerals. The important atomic and physical properties of this group element, along with their electronic configuration. Electronic configuration. The valence shell electronic configuration of these elements is ns2 and p3. The s orbital in these elements is completely filled and p orbitals are half filled, making their electronic configuration extra stable. Atomic and ionic radii. Covalent and ionic radii increases in size down the group. There is considerable increase in covalent radius from N to P. However, from arsenic to bismuth, as only a small increase in covalent radius is observed. This is due to the presence of completely filled d and or f orbitals in heavier members. Ionization enthalpy. Ionization enthalpy decreases down the group due to gradual increase in atomic size because of the extra stable half-filled p orbitals, electronic configuration and smaller size. The ionization enthalpy of group 15 element is much greater than that of group 14 element in corresponding period. Electronegativity. The electronegativity value in general decreases down the group with increasing atomic size. However, among the heavier elements, the difference is not that much pronounced. Physical properties. All the elements of this group are polyatomic. Dinitrogen is a diatomic gas where all others are solid. Metallic character increases down the group. Nitrogen and phosphorus are non-metal, arsenic and antimony metalloids, and bismuth is a metal. This is due to decrease in ionization enthalpy and increase in atomic size. Boiling point in general increases top to bottom in the group, but melting point increases up to arsenic and then decreases up to bismuth. Except nitrogen, all elements show allotropy. Chemical properties. Oxidation state and trend in chemical reactivity. Common oxidation state of these elements are -3, +3, and +5. The tendency to exhibit -3 oxidation state decreases down the group due to increase in size and metallic character. In fact, last member of group bismuth hardly form any compound in -3 oxidation state. Stability of +5 oxidation state decreases down the group. The only one well characterized of +5 oxidation state is bismuth compound. BIF5. Stability of +5 oxidation state decreases down and that of +3 state increases due to inert pair effect down the group. Nitrogen exhibits +1, +2, +4 oxidation states and also when it reacts with oxygen. Phosphorus also show +4 and +1 oxidation state in some oxoacids. In case of phosphorus, nearly all intermediate oxidation state disproportionate and +3 and -3 in alkali and acid. However, +3 oxidation state in case of arsenic, antimony and bismuth become increasingly stable with respect to disproportion. Nitrogen is restricted to a maximum covalency of 4. Only 4 orbitals are available for bonding. Anomalous properties of nitrogen. Nitrogen differs from the rest of the members of this group due to its smaller size, high electronegativity, high ionization enthalpy, and non-availability of d orbitals. Nitrogen has unique ability to form p-pi multiple bonds with itself and other elements having small size and high electronegativity. Heavier elements of this group do not form p-pi bonds as their atomic orbitals are so large and diffuse that they cannot have effective overlapping. On the contrary, phosphorus, arsenic, and antimony form single bonds as pp, while bismuth form metallic bond in elemental state. However, the single nitrogen bond is weaker than the single phosphorus bond because of high inter-electronic repulsion of the non-bonding electrons owing to the small bond length. As a result, the catenation tendency is weaker in nitrogen. Another factor which affects the chemistry of nitrogen is the absence of d orbital in its valence shell. Besides restricting its covalency to 4, nitrogen cannot form d-pi-p bond as the heavier element can. Phosphorus and arsenic can form d-pi bonds also with transition metals when their compound like these act as ligand. Reactivity towards hydrogen. All elements of group 15 form hydrides. Some of the properties of these hydrides are shown in table. The hydrides show regular gradation in their properties. Stability decreases from NH3 to BiH3. The reducing character of hydride increases. Ammonia is only mild reducing agent, while BiH3 is strongest reducing agent. Reactivity towards oxygen. All these elements form two types of oxides, E2O3 and E2O5. The oxide in the higher oxidation state of the element is more acidic than of lower oxidation state. Their acidic character decreases down the group. Reactivity towards oxygen. The oxides of the type E2O3 of nitrogen and phosphorus are purely acidic, that of arsenic and antimony amphoteric, and those of bismuth is predominantly basic. Reactivity towards halogen. These elements react to form two series of halides. Nitrogen does not form pentahalide due to non-availability of d orbital in its valence shell. Pentahalides are more covalent than trihalide. All the trihalide of these elements except those of nitrogen are stable. In case of nitrogen, NF3 is known to be stable. Trihalides except BiF3 are predominantly covalent in nature. Reactivity towards metals. All these elements react with metal to form their binary compound exhibiting -3 oxidation state, such as Ca3 and 2, calcium phosphide, sodium arsenide, zinc antimonide, magnesium bismuthide. Dinitrogen preparation. Dinitrogen is produced commercially by liquefaction and fractional distillation of air. Liquid dinitrogen distills out first, leaving behind liquid oxygen. In laboratory, dinitrogen is prepared by treating an aqueous solution of ammonium chloride with sodium nitrite. Small amount of NO and HNO3 are also formed in this reaction. These impurities can be removed by passing the gas through aqueous sulfuric acid containing potassium dichromate. It can also be obtained by thermal decomposition of ammonium dichromate. Very pure nitrogen can be obtained by thermal decomposition of sodium or barium azide. Properties: Dinitrogen is a colorless, odorless, tasteless, and non-toxic gas. It has two stable isotopes. It has a very low solubility in water and low freezing and boiling points. Dinitrogen is rather inert at room temperature because of high bond enthalpy of triple bond. Reactivity, however, increases rapidly with rising temperature. At higher temperature, it directly combines with some metal to form predominantly ionic nitrides and with non-metal covalent nitride. It combines with hydrogen at about 773 Kelvin in the presence of catalyst. Dinitrogen combines with dioxygen only at very high temperature to form nitric oxide. The main use of dinitrogen is in manufacturing of ammonia and other industrial chemical containing nitrogen. Ammonia. Ammonia is present in small quantity in air and soil where it is formed by decay of nitrogenous organic matter. Example, urea. On a small scale, ammonia is obtained from ammonium salts which decompose when treated with caustic soda or lime. On a large scale, ammonia is manufactured by Haber's process. In accordance with Le Chatelier's principle, high pressure would favor the formation of ammonia. Optimum conditions for production of ammonia are pressure of 200 into 10 raised to power 5 Pascal and a temperature of 700 Kelvin, and use of a catalyst such as iron oxide and small amount of K2O and Al2O3 to increase rate of attain of equilibrium. Properties: Ammonia is a colorless gas with a pungent odor. Its freezing and boiling points are 198.4 and 239.7 Kelvin respectively. In the solid and liquid state, it is associated through hydrogen bonds, and in case of water, and that accounts for its higher melting and boiling points than expected on the basis of its molecular mass. Ammonia molecule is trigonal pyramidal with nitrogen atom at the apex. It has three bond pair and one lone pair of electron as shown in structure. Ammonia gas is highly soluble in water. Its aqueous solution is weakly basic due to formation of hydroxide ions. It forms ammonium salt with acids as a weak base. It precipitates the hydroxides of many metals from their salt solution. The presence of a lone pair of electron of nitrogen atom of the ammonia molecule makes it a Lewis base. It donates the electron pair and forms a linkage with metal ion, and the formation of such complex compound finds application in detection of metal ions. Nitric acid. Nitrogen forms oxoacids such as H2N2O2, hyponitrous acid, nitrous acid, nitric acid. Amongst them, nitric acid is the most important. In the laboratory, nitric acid is prepared by heating KNO3 or NaNO3 at concentrated H2SO4 in a glass retort. On a large scale, it is prepared mainly by Ostwald's process. This process is based upon catalytic oxidation of ammonia by atmospheric oxygen. Nitric acid thus formed combined with oxygen gives NO2. Nitrogen dioxide so formed dissolves in water to give nitric acid. NO thus formed is recycled and the aqueous HNO3 can be concentrated by distillation. Properties: it is a colorless liquid. Laboratory grade nitric acid contains 68% of HNO3 by mass and has specific gravity of 1.504. In gaseous state, it exists as a planar molecule with structure as shown. In aqueous solution, nitric acid behaves as strong acid giving hydronium and nitrate ions. Concentrated nitric acid is a strong oxidizing agent and attacks most metals except noble metals such as gold and platinum. The product of oxidation depend upon the concentration of the acid, temperature, and nature of the material undergoing oxidation. Zinc react with dilute nitric acid to give N2O and with concentrated acid to give NO2. Some metals do not dissolve in concentrated nitric acid because of formation of a passive film of oxide on the surface. Concentrated nitric acid also oxidizes non-metal and their compound. Brown ring test. Familiar brown ring tests for nitrate depend on ability of Fe2 plus to reduce nitrate to nitric acid, which react with iron to form brown colored complex. The test is usually carried out by adding dilute ferrous sulfate solution to an aqueous solution containing nitrate ion. Then carefully adding concentrated sulfuric acid along the sides of the test tube. A brown ring at the interface between the solution and sulfuric acid layer indicate presence of nitrate ion in solution. The major use of nitric acid is in manufacture of ammonium nitrate for fertilizer and other nitrate for use in explosives and pyrotechnics. Phosphorus allotropic. Phosphorus is found in many allotropic forms. The most important one are white, red and black. White phosphorus is a translucent white waxy solid. It is poisonous, insoluble in water but soluble in carbon disulfide and glows in dark. It dissolves in boiling NaOH solution in an inert atmosphere. While phosphorus is less stable and therefore more reactive than the other solid phases under normal conditions because of angular strain in P4 molecule where angles are only 60 degrees. It readily catches fire in air to give dense white fumes. It consists of discrete tetrahedral P4 molecules. Red phosphorus is obtained by heating white phosphorus at 573 Kelvin in an inert atmosphere for several days. When red phosphorus is heated under high pressure, a series of phases of black phosphorus are formed. Red phosphorus possesses iron-gray luster. It is odorless, non-poisonous, and insoluble in water as well as in carbon disulfide. Chemically, red phosphorus is much less reactive than white phosphorus. It does not glow in the dark. It is polymeric, consisting of chains of P4 tetrahedra linked together in manner. Black phosphorus has two forms, alpha black phosphorus and beta black phosphorus. Alpha black phosphorus is formed when red phosphorus is heated in sealed tube at 803 Kelvin. It can be sublimed in air and has opaque monoclinic or rhombohedral crystals. It does not oxidize in air. Beta black phosphorus is prepared by heating white phosphorus at 473 Kelvin under high pressure. It does not burn in air up to 673 Kelvin. Phosphine preparation. Phosphine is prepared by reaction of calcium phosphide with water or dilute HCl. In laboratory, it is prepared by heating white phosphorus with concentrated sodium hydroxide solution in an inert atmosphere of carbon dioxide. When pure, it is non-inflammable but becomes inflammable owing to the presence of P2H4 and P4 vapors. To purify it from the impurities, it is absorbed in hydrogen iodide to form phosphorium iodide, which on treating with potassium hydroxide gives phosphide properties. It is a colorless gas with rotten fish smell and is highly poisonous. It explodes in contact with traces of oxidizing agents like nitric acid, chlorine, and bromine vapors. It is slightly soluble in water. The solution of pH 3 in water decomposes in presence of light, giving red phosphorus and hydrogen. When absorbed in copper sulfate or mercury chloride solution, the corresponding phosphides are obtained. Phosphine is weakly basic, like ammonia gives phosphinium amount compound with acids. Phosphorus halides. Phosphorus forms two types of halides. Its preparation. Phosphorus trichloride preparation. It is obtained by passing dry chlorine over heated white phosphorus. It is also obtained by action of thionyl fluoride with white phosphorus. Properties. It is a colorless oily liquid and hydrolyzed in the presence of moisture. It reacts with organic compounds containing OH groups such as CH3COOH, C2H5OH. It has a pyramidal shape in which phosphorus is sp3 hybridized. Phosphorus pentachloride preparation. Phosphorus pentachloride is prepared by reaction of white phosphorus with excess of dry chlorine. It can also be prepared by action of SO2Cl2 on phosphorus. Properties. PCl5 is a yellowish white powder and in moist air it hydrolyzes to POCl3 and finally gets converted to phosphoric acid. When heated it sublimes but decomposes on stronger heating. It reacts with organic compound containing OH group, converting them to chloroderivatives. Finally divided finely divided metals on heating with PCl5 give corresponding chlorides. It is used in the synthesis of some organic compounds. In gaseous and liquid phase, it has a trigonal bipyramidal structure. The three equatorial phosphorus chlorine bonds are equivalent while two axial bonds are longer than equatorial bond. This is due to axial bond pairs suffer more repulsion as compared to equatorial bond. Oxoacids of phosphorus. Phosphorus form a number of oxoacids. The important oxoacid with their formula, method and preparation and presence of some characteristic bond are given. Hypophosphorus, orthophosphorus, pyrophosphorus, hypophosphorus, orthophosphoric, pyrophosphoric, metaphosphoric. The composition of the oxoacids are interrelated in terms of loss or gain of water molecules or oxygen atom. In oxoacids, phosphorus is tetrahedrally surrounded by other atoms. All these acids contain one phosphorus oxygen double bond and at least one phosphorus hydroxide bond. The oxoacid in other phosphorus has lower oxidation state contains in addition to phosphorus oxygen double bond and phosphorus hydroxide bonds. These acid in plus 3 oxidation state of phosphorus tend to disproportionate to higher and lower oxidation states. The acid which contain phosphorus hydrogen bond has strong reducing properties. Thus, hypophosphorus acid is good reducing agent as it contains two phosphorus hydrogen bond and reduces. These phosphorus hydrogen bonds are not ionizable to give hydrogen ion and do not play any role in basicity. Only those hydrogen atoms which are attached with oxygen in phosphorus hydroxide form an ionizable form are ionizable and causes basicity. Group 16 elements: oxygen, sulfur, selenium, tellurium, polonium constitute group 16 of periodic table. This is sometimes known as group of chalcogens. The name is derived from Greek word for brass and points to association of sulfur and its congeners with copper. Most copper minerals contain either oxygen or sulfur, and frequently the other members of the group occurrence. Oxygen is most abundant of all the elements on Earth. Oxygen forms about 46.6% by mass of Earth's crust. However, abundance of sulfur in Earth's crust is only 0.03 to 0.1%. Combined sulfur exists primarily by as sulfates such as gypsum, Epsom salt, barite. Sulfides are such as galena, zinc blende, copper pyrite. Traces of sulfur occur as hydrogen sulfide in volcanoes. Organic materials such as egg protein, garlic, onion, mustard, hair, and wool contain sulfur. Important atomic and physical property of group 16 along with electronic configuration. Electronic configuration: the element of group 16 have 6 electrons in outermost shell and have ns2 and p4 general electronic configuration. Atomic and ionic radii: due to increase in the number of shells, the atomic and ionic radii increases from top to bottom in the group. The size of oxygen atom is however exceptionally small. Ionization enthalpy: ionization enthalpy decreases down the group. It is due to increase in size. However, the elements of this group have lower ionization enthalpy value compared to those of group 15 in the corresponding period. This is due to the fact that group 15 elements have extra stable half-filled p orbital electronic configuration. Electron gain enthalpy: because of the compact nature of oxygen atom, it has less negative electron gain enthalpy than sulfur. However, from sulfur onwards the value again becomes less negative up to polonium. Electronegativity: next to fluorine, oxygen has the highest electronegativity value amongst the elements within the group. Electronegativity decreases with an increase from oxygen to polonium. Physical properties: some of the physical properties of group 16 elements are given. Oxygen and sulfur are non-metal. Selenium and tellurium metalloids. Polonium is a metal. Polonium is radioactive and short-lived. All these elements exhibit allotropy. The melting and boiling point increase with an increase in atomic number down the group. The large difference between the melting and boiling point of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as diatomic molecule, whereas sulfur exists as polyatomic molecule. Chemical properties, oxidation rate and trends in chemical reactivity. The elements of group 16 exhibit a number of oxidation states. The stability of -2 oxidation state decreases down the group. Polonium hardly shows -2 oxidation state. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -3, except in case of OF2, where its oxidation state is +2. Other elements of the group exhibit +2, +4, +6 oxidation states, but +4 and +6 are more common. Sulfur, selenium, and tellurium usually show +4 oxidation state in their compound with oxygen and +6 with fluorine. Bonding in +4 and +6 oxidation state are primarily covalent. Anomalous behavior of oxygen. Anomalous behavior of oxygen, like other members of Q block present in second period, is due to its small size and high electronegativity. One typical example of effect of small size and high electronegativity is presence of small, strong hydrogen bonding in water, which is not found in hydrogen sulfide. The absence of d orbital in oxygen limits its covalency to 4 and in practice rarely exceeds 2. On the other hand, in case of other elements of the group, the valence shell can be expanded and covalence exceeds 4. Reactivity with hydrogen. All the elements of group 16 form hydride of the type H2E. Some property of hydride are given. Their acidic character increases from H2O to H2TE. Increase in acidic character can be explained in terms of decrease in bond dissociation enthalpy down the group. All hydrides except water possess a reducing property, and this character increases. Reactivity with oxygen. All these elements form oxides of the EO2 and EO3 types. Ozone and sulfur dioxide are gases, while selenium dioxide is solid. Reducing property of dioxide decreases from SO2 to TeO2. SO2 is reducing while TeO2 is oxidizing agent. Both types of oxides are acidic in nature. Reactivity towards halogen. Elements of group 16 form a large number of halide of the type EX6, EX4, and EX2. The stability of halides decreases in the order fluorine, chlorine, bromine, iodine. Amongst hexahalides, hexafluorides are the only stable halides. Hexafluorides are gaseous in nature. They have octahedral structure. Sulfur hexafluoride SF6 is exceptionally stable for steric reasons. Among tetrafluorides, SF4 is a gas, SeF4 is a liquid, and TeF4 a solid. This fluoride has sp3d hybridization and this trigonal bipyramidal structure in which one of the equatorial position is occupied by lone pair of electrons. This geometry is also regarded as seesaw geometry. All elements except selenium form dichlorides and dibromides. These dihalides are formed by sp3 hybridization and thus have tetrahedral structure. The well-known monohalides and are dimeric in nature. Dioxygen preparation. Dioxygen can be obtained in laboratory by heating oxygen-containing salts such as chlorates, nitrates, and permanganates, by thermal decomposition of oxides of metal low in electrochemical series and higher oxides of some metals. Hydrogen peroxide is readily decomposed into water and dioxide by catalysts such as finely divided metals and manganese dioxide. On large scale, it can be prepared from water or air. Electrolysis of water leads to release of hydrogen at cathode and oxygen at anode. Industrially, dioxygen is obtained from air by first removing carbon dioxide and water vapor, and then the remaining gases are liquefied and capsules distilled to give dinitrogen and dioxygen.